Doo-doo-doo. Okay, we are live. So today we're going to be going over sorting and searching algorithms. So I guess our first question is, are you familiar with that? Is that something you've done in school or anything? Oh, Dana?
Her mic's yes, briefly.
Ah, okay. So would you want us to go over, I suppose, in depth about the algorithms themselves, or would you just prefer like a brief overview and then we could just dive into some problems? Okay, sounds good. So I guess you want to go first, Hannah, or should I? It doesn't really matter.
It doesn't matter. I guess I can start.
Okay.
Um, so first we are going to talk about searching. And basically on the AP Comp Sci test, you guys are going to have to know how to trace through different searching and sorting algorithms. And so you said you had already sort of heard of searching and sorting algorithms, and so I'm sure you know they basically do their name. They either search for something or they sort a set of elements. So first we're going to talk about searching algorithms. And so the first one that is on the AP Comp Sci test is a sequential search. And a sequential search is pretty basic. You just start at the beginning of your list, and if the element at the first index matches what you are looking for, then you return that. If not, you move on to the next element and you return that, and you basically just keep going down the line of your list of elements until you find the one that you are looking for. And so to do a sequential search, the data does not have to be ordered. And so then the next type of search that you guys are going to need to know for the AP test is a binary search. So one example to kind of explain a binary search is to think about a dictionary. So let's say you had a dictionary and you were trying to search for a specific word, but obviously there are a lot of different pages. But the thing about a dictionary is that all of the words are in order. They're alphabetical. So if you have a word that you already know it's ordered in a certain way. And so this can make it easier to search for it versus if the data wasn't already ordered. So basically how a binary search works is you start at the middle. So you compare the value that you are looking for with the middle value, and depending on if the value in the middle is greater than or less than the value you are looking for, then you go to the right or to the left. So if the value is greater than what you are looking for, then you're going to look at the lower half of your list. Or if the value in the middle is less than the value that you are looking for, then you're going to go to the other half of the list. And basically, you're just going to keep going to the middle of each part and keep making it smaller and smaller and smaller until you find the element that you are looking for. So Asta actually found something that visualizes this. That
It's really cool.
can you guys see my screen?
Hmm.
Okay. So binary search. And so this is going through the code for a binary search right here. Here, can we do it maybe a
Yeah.
little bit slower?
And you, in the upper left-hand corner, you can put in the number that you want to search for.
Okay, so let's say that we are searching for the number 74. Binary search. So as you can see, it just went to the middle of the array over here, and it realized that it was smaller. Basically keep going and finding the middle of each section and deciding whether the value it's looking for is less than or greater to the middle until it gets to that value 74. Here, wait, maybe, oh, you can pause it. Okay, I'm gonna do it one more time and we can pause it each time it goes through. Binary search. Okay, so we're searching for 74 up here. And so this is our array that we are searching through. And so we are basically first going to just find the middle value of the whole array, which is 413. Then what we're going to do is compare that middle value, 413, to the value that we're searching for, 74. And since 74 is less than 413, we're going to make our problem smaller by only using the lower half of the array. Because since the array is already ordered, we know that the value that we're looking for is going to be somewhere in the lesser half, not the greater half of the array. So we keep going. So then we found the middle of the lower half of the array, which is 267, and 74 is still less than 267. So now we're going to move to the lower half of our half of an array. Okay, so now we get to the middle of this, which is 121. 74 is still less than 121. So now we're going to just concentrate on this part of the array. And so we can see that our middle value is finally 74, which is what we are looking for. So that is what we are going to return. All right, so does that all make sense? Yes?
Cool.
Okay. Asta, do you think we should go into sorting then? Or because I had like a couple like quick ebook examples, but I guess if you understand it, then we can
Maybe let's just do the questions just to make sure.
Okay.
And clear anything up before moving on to another topic. So.
Okay. So in the ebook, there are some examples on binary search. I can just send the link in the chat. And so I guess if you want to take a minute or two to just do 1, 2, and 3, and then we can go over them if you have any questions. You can just like type in the chat so we know that you got to it and when you're done.
Okay, cool. Oh, Hannah, you're frozen. Okay, you're good now.
Can you see me now?
Yeah.
So did you get all the questions, Dana? Because I think that on the ebook, you can go and you can check them yourself. Or are there any that you weren't sure about that you want us to go over? Does it matter if this fits? Why or why not? I don't think it does matter if a list contains duplicates, right, Asta?
I think all that matters is that it's in order.
Yeah, as long as it's in order, it's okay.
Because, I mean, it's still going to cycle through the binary search, and
Yeah,
it wouldn't ruin it because of that.
yeah, like it would still taking the first.
You're cutting up a lot.
Me?
Yeah. Hannah? Maybe try turning off your video for a little bit.
Oh, am I here now?
Yeah. There's like two of you. It's weird. But anyway. Yeah, but this one is a lot better.
Okay, good. Oh yeah, I see that there's two of me. That's weird.
So
yeah,
did you catch anything that we said, Naraz? Because I don't know how much you were able to hear because of that weird glitching thing. Did you change Wi-Fi networks?
no.
Weird. You're like frozen there too.
Oh, I heard most. Am I
Oh,
still frozen?
no. But like your other one is, which is weird.
Oh, is it like still on my face? The other one?
Yeah.
Because on my screen, it's showing like my Google picture.
Oh yeah, it's just your face like frozen. I'm gonna try.
Oh, that's weird.
I can leave it there because I don't want to ruin it. Otherwise, I could try ejecting you from the chat, but I'm afraid that'll eject.
Oh wait, it just went away.
Yeah. Okay.
That's
Cool.
weird. Oh, I heard most of it. Okay, so basically, yeah, fine if you have duplicates because that's not going to affect how the binary search works because comparing it. Yeah, so if it's not that, it's still going to find the element eventually.
Mm-hmm. Does it actually find the first instance of the element, or would it find the second? Huh.
Asta, you're like breaking up now.
Oh, it sounds like you are. Uh, hey, Naraz, can you still hear me? Okay. I think it's just you, Hannah.
Huh?
I
Sorry
think it's
again.
I think it's just you. Like, I think there's something wrong with the Wi-Fi network.
Probably, honestly, Maryland.
Have everything except good Wi-Fi connection.
Here, okay. Okay, I'm gonna try like connecting to my phone's Wi-Fi instead and see if that works better.
Okay. I guess in the meanwhile, do you have any other questions for us? Otherwise, we can start going the sorting algorithms. Okay, sounds cool. So the three sorting algorithms that AP will want you to be familiar with at least is the selection sort, insertion sort, and merge sort. Um, Merge sort is traditionally what people find the most difficult because it involves recursion. Uh, and I have to admit, looking at the code is a little bit difficult, but I think so long as you have an idea of what the code is supposed to do and like what the sort is supposed to do, it helps go a really long way. So the selection sort is the one that's traditionally like really easy to understand. You essentially say you have a whole array, right? You're gonna find the smallest element of that array, and once you find it, you're gonna swap it with the 0th spot. And then that way, the smallest element is now in the beginning. And then what it does is the algorithm will start searching from the first element down to the last one. It's going to find the smallest one in that range. And then it's going to swap whatever is the next smallest element with the first spot. And then it's going to go to the second, and so on and so forth. So what it's essentially doing is like going through the array, finding the smallest, putting it in the beginning, and then finding the next smallest and putting it in the next spot, and so on and so forth. And you can reverse it. So if you want to find the biggest element and put it in the first spot, and then the next biggest element and put in the second spot. And the only real difference that's going to make is that it's going to go in descending order as opposed to ascending order. So there's that sort. That's essentially what it's doing. The next sort is an insertion sort. So what it does is it kind of sorts itself relative to the first position. So it's kind of like, okay, say we have an array. Let me like draw one quickly, just because it's easier to see this. Start really small. So 7, 20, 1, and 4. 1, 2. So say we have this array right here. So what the sorry, what the insertion sort is going to do is be like, okay, let's say that the first position, the 0th position is set. So we're going to sort the next element relative to that. So it almost kind of ignores the last two and just looks at the first two elements and says, okay, relative to 7, where does 20 go? And since 20 is bigger than it, we can just leave it here because 20 is greater than 7. So it makes sense that in increasing order that the 20 would come after. So it's like, okay, cool. Now let's look at the next element. So now relative to 7 and 20, where does 1 go? 1 would go before 7. So what it'll actually do is move the 1 to the 0th position, and it's going to push the other 2 over. So the array is now going to look like this. 1, 7, 20, and 4. And then what it's going to do is look at the next element, which is 4, and says, okay, relative to 1, 7, and 20, where does 4 go? So it'll go after 1, but before 7. So it's actually going to insert it into that spot. So it's going to insert it into the 1 position and push the other 2 down. And so you end up having 1, 4, 7, and 20. And so now since you've already examined the last element in the array, it knows to stop then. And so this is going to be your finally sorted array. One of the important things to note is that in each loop of the insertion sort, the beginning parts of the array are already sorted. So what I mean by that is 7 is in increasing order against itself. 1 and 7 are in increasing order against itself. And 1, 4, 7, and 20 are all in increasing order against it, the section. So you'll always have a portion of the array that's actually in the correct order. It's just about getting the other stuff in correct order. Do you have any questions with that before we go into merge sort? Because that's traditionally one of the more difficult ones. and want to make sure you like are solid on these ones. Oh, any questions, Noraz? Oh, sorry, Dana? Oh, okay. Similar to sorting a hand of cards, but not really sure how quite to visualize that. Oh, I wish I had some cards on me right now, actually.
Oh, actually, I have cards. But
Yo, solid.
I think I have cards. Maybe. Actually, maybe not.
I have Uno cards, but I don't think that serves our purpose.
They're unopened.
Hey!
So, okay. I can open them. Maybe. We'll see. Wow. I can't believe I haven't used these yet, actually.
This weekend, before the exams start coming up.
Oh, yeah. Oh, man. Actually, I have one on Monday, but
oh my god. I'm so sorry.
yeah, it's okay.
So it goes.
Oh wait, I have scissors. Okay, so basically you can view trying to sort a deck of cards as insertion sort. Because so basically you have, oh actually these are all probably in order though already, since yeah it is in order. Okay, so let's just take like spades, and let's say like they're not in order. So this is like basically you could visualize all of these cards as like your array, and basically this is like insertion sort, because what you're going to do is, actually let's do less than that, let's just do like 6 just to make it easier. So you have your cards, and basically you can view this as insertion sort because okay, so basically you're going to start with like, so let's say I'm looking at the cards down the line, and so I start like, if I had this in my hand, then I would start with a 7, right? And so now I just have one card. And so this is the first element in my new set of sorted cards. So I just have a 7 here. And then I'm going to look at the next card, which is a 3. So then I'm going to take this 3 and I'm going to compare it to the other card I have. And 3 is less than 7, so I'm going to put it to the left. And then I'm going to keep doing that. So then I take the next card on top, which is an 8, and I'm going to compare my 8 with my 3 and the 7, and the 8 is greater, so it's going to go over here. And so basically it's different than selection sort because I'm not looking at like my whole deck of unordered cards and trying to figure out first like where the smallest card is. Instead, I'm just taking whichever one I have on top, and I'm inserting it in its order that it goes into the new deck of sorted cards. Does that make sense? Yeah? Okay, good.
Oh, cool. Okay, so merge sort is the last one, and that one uses recursion. So you'll generally be able to identify a merge sort basically because it'll have like around 2 to 3 methods, one of them being like a merge helper, and then the second one usually being the merge sort itself. So the idea is, and it's easier to do this with an example. So say we got this array of, let's do like 6 elements. 0, 1, 2, 3, 1, 2, 3, 4, 5, 6. Okay, so I'm just gonna put in random numbers. Okay, so let me put the indices. 3, 4, 5. Okay, so say we have this array. So it has the following numbers, and we're gonna do a merge sort on it. So what the merge sort is gonna do is that it's gonna recursively keep on breaking the array apart until you have an array of 1 with only 1 element inside of it. So it's first gonna break it in half. 1, 2, 1, 2, 3, 4, 5, 6. Yeah. So it's gonna break it into little arrays of 3. So it'll be 7, 9, and 42, and that's going to be one array of size 3. And then 0, 2, and 8 are going to be a second array. And then what it's going to do is, depending on how the algorithm is coded, it's either going to break it into one, like first array will be like of size 2, and then the second one will be size 1, or vice versa. I don't think it really matters. So it'll break this apart into, I'm just going to do, the first array is going to be 1, and the second one is going to be of size 2. And like it will be easier to see what I mean when I draw it out. So yeah, so sometimes they'll do like 2 elements here and then 1 element for that one. But I honestly don't think it matters so long as you get the idea. So it's basically going to keep on breaking it until you only have like boxes with just 1 element in it. So we have 1 more to go. Breaking up the other ones into just arrays of 1. Okay, so now we got these beautiful arrays, and they only got 1 box. And in the 1 box, it's going to have 1 number. So now what it's going to do, after it's broken everything down, is it's going to join these in pairs and then sort them properly. And then keep on joining them in pairs and then sorting them. So what I mean is, it's going to combine the 7 and the 9 into 1 array of size 2 and then make sure they're in the right order. And then same for 42 and 0 and 6 and 8. So when we combine them, we know 7 and 9 are in the right order. We would have to swap 0 and 42, and 2 and 8 are in the right order. So now what it's going to do is, wait, Hannah, do you know if it breaks apart this one and then makes it 3 and 3, or does it just join one of like the 1 into 1 array of 4 and then leaves the other 2 and then joins that later? I'm actually not sure. I think it makes more sense if it just joined these 2 and then joins this one after.
Yeah, I'm pretty sure, because like if you had an even number, then it would join like these two and then them together. So yeah, I think so.
Yeah. Sorry for the bad example I made up, Dana. But the idea is that like it, like say we had another like box here, it would join these 2 together then. So for the sake of this example, I'm just going to assume it joins these 2 together and then leaves this one off to the side. So this array is going to be 1 big one of size 4. And it's going to be properly sorted. So it'd be 0, 2, 8, and 42. We still have 7 and 9. And then I'm going to have to go to the side. But then it's just going to basically join these 2 arrays now into 1 grand array that is properly sorted of size 6. 0, 1, 2, 3, 4, 5. and 0, 2, 7, 8, 9, and 42. So this is going to be like your final answer. So you're going to have a properly sorted array after like doing all these little deconstructions and then reconstructions. The drawbacks of the merge sort is that it's very memory intensive because you need to do many recursive calls first of all, and then after that you need to be making a new array because you make like a copy array and then break all this down and then resort it and then return like a new array. But I believe that it is pretty fast. So it does have that going for it. So do you have any questions on that? Otherwise I found this really cool visualizer that kind of shows how it works. So I can display that. Oh, how does the array reconstruct in order after the subsets of 2 or more elements? I believe, let me see. I'm trying to look at the actual code itself to elucidate that.
I think it just like compares them one by one in order, but
Yeah, it looks like it sorts it within like each time it rejoins them. Yeah, that's what I would say. I have to admit, in all honesty, like after the AP exam, I've never needed a merge sort.
yeah.
So
Yeah, like as long as you know kind of the algorithm
you'll be
behind
fine.
each searching and sorting method, like as long as you know kind of how it works, then once you look at the code for it, you'll be able to see like, oh, so this part is like doing this and this part is doing that. And that'll make it easier to go through.
And also, for the AP exam itself, I don't think they really do tracing. Like, from what I remember doing the AP exam in junior year, it was that, like, I was able to do really, like, okay on the questions. And I had no clue about how the code actually worked. I just knew, like, how it was supposed to work, and I was able to answer all the questions from there. Not saying that's a good thing, and obviously you should try to understand the code, but it is not of the highest priority. But yeah, I think it just swaps and makes sure and does it in order. So I know not the best explanation, but any other issues or questions that you had with it? Oh, they have questions on those?
No, so I don't think there's any big O notation questions on the AP test, right?
They're not supposed to be.
Yeah. So big O notation is basically just referring to how much time each algorithm takes, because obviously when you're creating a program in real life, you want it to be as efficient as possible. And depending on just what you're programming and what the different data is that you're using, different sorting and searching methods are going to be more efficient than other ones.
Yeah.
So, for example, well, I guess if you don't like know what big O notation is like at all, like we shouldn't really get into that. But it's basically just determining how time efficient each one is.
Yeah, it's based on the number of elements in the data set. So It's like if I have this huge data set in relation to how big it is, how long will it take to process through it? So I don't know if that even makes sense to you right now, but the idea is like the bigger the array, the longer it is to process through each element. So big O is just referring to the efficiency, like Hannah said. Okay, cool. So I guess let's look at a visualizer for this. So I will share my screen. So you can just see pretty pictures. Oh, wrong pretty picture. Okay. So let's create some random data here. So here we have just a random set of numbers, and we are going to sort it via selection sort first. So let's have this going a little bit slower. Ah, where did it go? Okay. What's going on? Okay, can you guys see the screen?
Mm-hmm.
Okay, something happened, but it's all good now. So let us get started. So it's going to be selection sort. So now what it's doing is it's going to be comparing, and I can send you the link because it's actually a really good way to look at the code. It's looking through each of the elements in the array and trying to find which one is the smallest. So it's noting in pink what it finds to be the current smallest element. And then it's swapping them. So now it's going to do it again to find the smallest element from 44 to 48. So from the first indice all the way up until the end. So I'm going to just pause this and speed it up just a tad. Yep, so it's going to keep on going and doing that. So now it's going to look from 38 and it's going to go up until the end. Pause, speed this up. So as you can tell, this isn't the most efficient algorithm because you're searching through the array multiple times. And so when they're talking about best case and worst case, your best case would be if this is, I guess, already sorted. Even then, it's still going to search through the whole array multiple times. So I think the best case and the worst case would be exactly the same. So that's the idea for it. Yeah. So now let's look at the insertion sort. So what we can see here is that what it's doing is setting 3 as like your starting point, and it's looking at 44 and being like, okay, in relation to 3, where should 44 go? It should go afterwards. And so it keeps the elements in order. And now it's going to do the same with 38. So relative to 3 and 44, where is 38 going to go? And it would go in between. So we're going to see that happen. So we can see that it pushes 44 to the side, opening up a gap where the 38 goes. And now with the 5, it's going to see, okay, it has to go in between 3 and 38. So it's going to push these two over and put 5 in the gap where 38 was. And it's going to keep on doing this sort of pattern. Okay, in the interest of time, I'm just going to skip over to the merge sort now. So let's make sure this one goes a little bit slower. Somewhere around there. Sort. So wait, actually, let me go back. Okay, so the first thing it's doing, as we can see right here, is like trying to break it up into, and it says right here, breaking up the array into partitions of 1, and just, they do it by different shades of color. Personally, I don't like how they do it here, just because 3 and 44 look like the exact same shade to me, but I think it's just because, like, I'm not very good at seeing between shades. But the idea is that it's going to break apart into arrays of 1, each element being its own array. And so now what it's doing is that it's copying 3 into a new array. And we can see that it's like sorting them and like joining them in proper order. And same idea here. And now it's a different representation than how I drew it, but it's breaking them apart now into arrays of 2 and sorting them properly. And in this particular algorithm, the way they're doing it is that they're joining it immediately into 4 and then so on and so forth. So now it's joining up into arrays of 4 now and sorting them. So now it's going to join these two. Oh, sorry. It's going to join all of these together. In all honesty, I did not learn the merge sort with this particular algorithm, but the idea is still there, that it's breaking it apart into arrays of 1, joining them together into 2s, and then 4s, and then so on and so forth until you get the whole array. So I'm going to stop screen sharing now. Do you want to go into example problems now?
Sure, unless, do you have any other questions before we get into them?
Okay.
All right. So first, I have just 2 conceptual questions that you can answer. So I'm going to share my screen. Okay. So Asta, can you tell me what is in the chat? Okay. So this is the first question. An algorithm for searching a large sorted array for a specific value x compares every third item in the array to x until it finds one that is greater than or equal to x. When a larger value is found, the algorithm compares x to the previous 2 items. If the array is sorted in increasing order, which of the following describes all cases when this algorithm uses fewer comparisons to find x than a binary search?
So let us know in the chat when you're done, and also, I guess, what answer you got. Okay, so Dana said, I think the answer is D, but I'm not sure.
Okay, so correct answer to this question is actually C, when x is very close to the beginning of the array. And so when you think about binary search is one of the most efficient searching algorithms, because it basically, instead of going through the whole array every single time to look for your specific value, you're going to keep cutting the problem in half each time. So for this specific algorithm, basically, so it says that the array is also sorted, and we're searching for x for every third item. So let's say that the element that we were looking for was very close to the beginning of the array. So it was one of the first 3 elements. That would mean that we would find the element that we are looking for on the very first pass of the array, because it would look at the 3rd element, and then it would look to see if that element is larger than the one we're looking for. Then it would look to the first 2, and then it would find it. And so that it would only have to go through its algorithm 1 time, versus if we were using a binary search to try to find an element at the beginning of the array, you would have to go through more than once, because when we are doing a binary search, we are going to the middle each time. And so it would probably take us a couple of passes through the algorithm in order to get to the beginning of the array. So that is why it's going to work best for the beginning of the array, better than a binary search. So it's not going to work best for what you said, D, because if it was very close to the end of the array, since we're comparing every 3 values, let's say that this array was of size like 90, that would mean that we would have to go through the whole array like 30 different times in order to get to the very end, since we're just comparing 3 elements at a time in order. Versus a binary search, since it's cutting the problem in half each time, it's still going to probably take a while, but it's not going to take as long as if we were to go through the whole array in the way that this specific algorithm is. Does that make sense?
She said, yep.
Okay. So this is the next problem. Unsorted array contains an unsorted list of integers, and a different array, sorted array, contains a list of sorted integers. Which of the following operations is more efficient for sorted array than unsorted array? Assume the most efficient algorithms are used.
Okay, so she says, I think the answer is B, because 1 and 3 aren't affected by whether or not the list is sorted.
Yep, exactly. Good job. 2 is the correct answer for that reason exactly.
Mm-hmm.
Okay, so for the next problem, number 15, An array of integer is to be sorted biggest to smallest using the insertion sort method. If the array originally contains these numbers, what will it look like after the third pass of the for loop?
She says, I'm not sure, but the answer seems like A to me.
Okay, you are close. The answer is actually B. So basically what is going to happen, we're doing insertion sort. So what that means is we're going to go through each element in our array and insert it in its proper place in our new list. So we're going to start with 1, and that's going to be the first element of our new list. And we're going to go to 7, and we're going to compare 7 to our first element of the list. And 7 is greater than 1, and we want to insert it in order from biggest to smallest. So here, wait, let me write it down here. Trying to, oh, did I delete it by accident?
I think so.
Okay. Okay. There we go. So for our first pass, we're going to compare, so we already have 1, and we're going to compare it to 7. And 7 is greater than 1, and we want to sort our new array from biggest to smallest. So that 7 is going to swap places with the 1. And so we're going to have those as our new list, and then just the other ones in the order that they were in. So that is after the first pass. And then in the second pass, we're going to look at our next element, which is 9. 9 is greater than 1 and 7, so it's going to be inserted at the front of the list. And then we're left with 5, 4, and 12. And then for our third pass, we're going to look at 5. And so if we compare 5 to 1, 5 is going to be greater than 1, but less than 7. So 5 is going to be inserted into its proper place in the list, and we're going to be left with 4 and 12 still unsorted. And so that's how we get B for that one. Does that make sense?
Yep.
Okay. So I think that that's all the practice problems we have time for today. Do you have any other last minute questions? And if you want to go over more examples, there's also a problem set in the ebook that you can look at.
Mm-hmm. Oh, cool. She said no, thank you. Oh yeah, you can see it now. What am I doing? Okay. Um.
Right.
So I guess last minute reminders. The in-person meeting is going to be this Sunday. So be sure to tune in online or in person. In person is always better, if possible. So yeah, if you have other questions, I guess we'll call it a night.
All right. We'll see you. Good night.
Good night.
Bye.